density is 1/4. Yes? Any question, guys? Okay. B, I need to find the probability that x between 1.3 to 5. Okay. 1.3 and then 5 out here. So probability is area. From 3 to 5, there's no area because the density is 0. So this is the same thing. This is the same thing of saying that I'm integrating from 1 to 3, but only up to 3, right? Because I only have area there, right? From 3 to 5, there's no area. 1/4 x dx. Okay. And so, again, I put out the 1/4, and then n times of x is x squared over 2 from 1.3 to 3. Right, so you get 1/8, 9 minus 1.3 squared, so you get about 0.9 something. Had you, if you set up the problem like this, 1.3 to 5, 1/4 x dx, you're going to get 2 point something. And that cannot be representing probability, right? I'm looking for probability, and probability cannot be above 1. Yeah? So when you get something like this, you have to realize that you did something wrong, right? The fact that some of you just submitted this value, that's kind of scary. How can you turn in a value of 2 point something for probability? Okay, so be careful, guys. Yeah? C, I'm asking for the expected value x. So, well, it's x times the density. The density is 1/4 x dx from 1 to 3. Right, you put out 1/4, and then you have an entire of x squared, which is x cubed over 3 from 1 to 3. So you got 112, 3 cubed, that's 27, minus 1, so you get 26 over 12, or 13 over 6. Okay. Very simple integration, and very simple to what we did in class as well, right? You do have to go back to the example we did in class and, practice over them and get ready for the quiz and exam questions, all right? Variance is EX squared minus square of AX. Okay, so I need to know what this number is. So I'm setting up this integral, right, as x squared times 1/4 x dx from 1 to 3. Again, so I'm pulling out 1/4, and inside I get x3 dx from 1 to 3. And antiderivative of x cubed is x4 over 4, 1 and 3. And so for 4, so that's 116. And then 3 to the 4th power, that's 81 minus 1, right? So 80 over 16, which is 5, right? So EX squared is 5. So that means that the variance of x is 5 minus the mean. The mean is 13 over 6 square. And then you get a number. So that's the quiz. Right. Things that we have done in class, probably many examples in class. So it's nothing new there. It's not hard, but you do need to practice. Okay. Any question for me? No question? All right, let's see. Let's moving on. We're going to be looking at chapter 6 today. In particular, I'm looking at the sampling distribution of the sample mean. The sampling distribution of the sample mean. And the title lengthy, it might not make much sense, but after one or two examples, you know what I'm talking about. All right, so this chapter is like, a transition chapter for moving from probability to statistics. What we have done so far, we learned the background of probability. And then once you have those sufficient background, we're going to move to statistics. We look into how to do statistics, and this kind of chapter serves like a bridge connecting the two topics, probability and statistics, the sampling distribution of the sample mean. Okay, so let's see. First of all, let me quickly mention what is the sample mean, all right? So what is the sample mean? The sample mean is the arithmetic mean of a sample, okay? That's the arithmetic mean of a sample. A sample is a set of numbers, that's all, right? So let's say if you have a data set like 3, 5, 3, 4, 10, 12, something like that. You have a set of numbers. Then from here, I can calculate the sample mean, right, which denoted as X bar, okay? The sample mean. That's arithmetic mean. So you add them up, divided by the number of observations. So that's 5. Yes? What you get here? 12, 24, 34 over 5. That's the sample mean. Right? That's the mean, it's the arithmetic mean of a given sample. That's the sample mean, right? That's simple. Okay. Let me start with an example that illustrates the concept of the sampling distribution. I got to kick out somehow. Need to connect my iPad back in. Okay, so let's consider the following distribution. Let's say I have a simple distribution. You know, 0, 1, 2, and then 0.2, 0.3, 0.5, right? So it's a valid distribution because the sum of the second row is 1, right? What this distribution means is that if I, let's say, you know, imagine this like a big bag of candies, right? 20% of those candy had number 0, or let's say color yellow, right? 30% red and 50% are blue, something like that. 2 for blue, 1 for red, 0 for yellow. If I randomly select a candy in there, then 20% of the time I'm going to get a yellow, 30% I'm going to get a red, and 50% I'm get a blue. That's what it say. That's what it means, right? Or I have coins of value 0, 1, 2, right? 20% of those coins are 0, 30% 1, so and so. Okay, it's simple that we can find, that if I need to find the mean, right? If I randomly select a number from this distribution, what's the average? What's the average? Right? Well, that's easy. That's 0 times 0.2, 1 times 0.3, and 2 times 0.5. Yes? And if I want to find the variance, so same thing, I'm going to calculate E of x squared minus, what's this number? Anyone? 0.3.
1.69.
Is that 1.3?
1.3.
1.3. So this is 1.3 squared. So I need to find E of x squared. Go ahead. Keep pressing you on how to calculate this stuff. Wow. Anyone else kind enough to turn on the video beside Calvin? Man, this is hard. This is hard. Thank you, Matt. All right. Okay, so E of x squared, anyone? 0 squared times 0.2, 1 square 0.3, 2 square times that, right? So that's 0.3 and then 4. So that's 2. 2.3, yes? So I'm getting 2.3 minus 1.3 squared. What is sigma squared? What is the variance? 0.61. 0.61. Okay, that's what we learned before. We know how to do it. We know how to find the mean. We know how to find the variance of a distribution. Okay, so now let's start talking about statistics. When you talk about statistics, means that you have data, you have sample, okay? You have set of numbers. Well, where do I get these numbers? Okay, I get my sample from a population, right? Some kind of population, some kind of distribution. Population is like distribution. So imagine this action now. All right, this distribution serves as my population. In my population, whenever this kind of population, when I randomly select a number from here, I either get 0 or 1 or 2 with respected probabilities, right? 20% of the time I'm going to get 0, 30% of the times I get 1, and 50% I'm going to get 2. All right, imagine that I'm gonna get 2 numbers from here. So I form a sample this is a sample of size 2, right? Let's learn the terminology. So when we switch to statistics, you know what I'm talking about. This represents a sample of size 2 selected from the given distribution. Yeah? Here we make things really small, really simple, so then we can do the calculation. In practice, we're not talking about sample of size 2. In practice, we might talk about sample of size 15, 22, 35, whatever, right? Sample of size 2 is meaningless, okay? You cannot say anything. There's not much value in there for you to say. All right, but anyway, if I have a sample of size 2, first of all, how many possible sample of size 2 that I can select from here? Well, it's not too bad, because let's say I can list all of my possible samples. One of them is 0, 0. I draw the first observation, x1, I get 0. I draw the second observation, I get 0 again. So that's one possible sample. Yeah? Here's another one, 0, 1, 0, 2. Yeah? Of course, I can also get 1, 0, 1, 1, or 1, 2. Yeah? Or I can also get 2, 0, 2, 1, and 2, 2. Is that okay, guys? Those are all the possible samples of size 2 that I can get from this population, from this distribution. Somehow I get kicked out again. Any IT person explain it to me why I got kicked out? Mirror my iPad with Zoom again. Okay, let's see. Next, I want to construct a column that that calculate the sample mean. And then the last column is the probability for each sample. Very simple. If I get a sample 0, 0, what is my sample mean?
0.
0. Justin, my screen is not frozen.
That was earlier. Sorry.
Oh, okay.
Thank you.
All right. So the sample mean, as I mentioned earlier, if you have a sample mean is just the arithmetic average, right? So if you have 0, the sample mean is 0. No question. If I have 0 and 1, the sample mean of the sample is 0.5, right? 0 plus 1 divided by 2. 0, 2, well, the sample mean is 1. Yeah? Now, for the probability, what's the represent the what's the problem getting 0 and 0? Well, if I put my hands in there, what's the chance that I'm getting number 0? That's 0.2. And then put my hands in there, I get a 0 again. So that's 0.2 again. So I get 0.04. Is that okay, guys? Zero and 1, so that's 0.2 and 0.3. So that's 0.06. 0 and 2, 0.2 and 0.5, that's 0.1. Okay, go on. Complete the table for me, please. Okay. 0.1, 0.5, 1, 1.5, yeah. Here 1, 1.5, and 2. So the sample means are easy to calculate. The problem getting 1 and 0, so 0.3, 0.2, so that's 0.06. 1 and 1, 0.3 and 0.3, so that's 0.09. 1 and 2, so 0.3 and 0.5, so that's 0.15. 2 and 0, 0.5 and 0.2, so that's 0.1. 0.5, 0.3, so that's 0.15. 0.5 and 0.5, so that's 0.25. Agree? All right. So what's going on here? When I draw a sample of size 2, okay, there's some important lesson to be learned from this here, right? And that's carried out to the remainder of the semester. When I draw a sample, any sample of any size, in particular here I'm talking about size 2, so that we can facilitate the so that the calculation is simple. But I can do any size, right? A size 3, size 5, size 10, whatever. So when I have a sample, right, when I draw a sample, and once I have a sample, I can calculate the sample mean. Yes. Now, are the sample means stay the same, or are they changing?
Like overall?
Are the sample mean stay the same? No.
No.
Are the sample mean stay the same? Are they changing?
They're changing.
They're changing, right? The sample mean is the mean of the respected sample. So it depends on what sample I get, correct? The sample mean is the average of that given sample. So if I have a different sample, likely I'm going to have a different, likely I'm going to have different value for the sample mean. So the sample mean is not a constant. The sample mean changing from sample to sample. Yeah. Here I have only 9 possible samples, but imagine instead of having a sample of size 2, if I have a sample of size 10, right, I'm going to have a lot of possible samples. Yeah, it's 2 to the it's 3 to the 10 power, right? Many possible sample. Right? This is 9 because it's 3 squared. Right? 3 times 3. If I have a sample of size 10, it's 3 to the 10 possible sample. It's too many to work with, right? So each sample, produce a sample mean, right? So sample mean is not constant. Sample mean is changing. The purpose of this chapter is to study how the sample mean changing. We want to study the distribution of the sample mean, or what we mean by the sampling distribution of the sample mean. Okay, so once I have a table like this, okay, you look it over, right? See that sample mean 0.5, 0.5, and 1, and 1, and 1, and 1.5. So I'm gonna put now the distribution for the table for the sample mean. Right, I look at these numbers. So what are the possible value for my sample mean in this case? 0. Yes. What else? 0.5. Yeah. 1, 1.5, and 2. Is that okay, guys? Now, what's the chance that X bar is 0? Well, that's why we calculate the probability here. Yes, X bar is, that's the only case, so that's 0.04. Yeah. What's the chance that X bar is 0.5? Well, you see X bar could be 0.5 here, or X bar could be 0.5 here. So you add up the probabilities. So that's 0.12. Right? Same thing for 1. I see 1 here, 1 here, and 1 here. So the probability would be 0.29. Okay. 1.5, 1.5, so that's 0.30. And finally 2, that's 0.25. And before I submit my answer, I'm going to check if the sum of the second row is 1. Do they sum up to 1?
Yes.
They sum up to 1. So it's the valid distribution. So this table shows how the distribution, how X bar is distributed. Sometimes X bar is 0 with 4%. Sometimes X bar is 0.5, 12%, 1, 29%, and so and so. So this is what we mean by this. This is what we mean by the sampling distribution of the sample mean. Is that okay, guys? Next, I want you to calculate the expected value of X bar. Right, the expected value of this table. So go ahead. Can you calculate the expected value of the table that we just constructed? Oops, I got kicked out again. Expected by X bar. That's 0.04 plus 0.5, 0.12 plus 1.29 plus 1.5.3 and 2.25. Did anyone get a number? Yeah.
1.3.
1.3. Right. This is sometimes we write as a mu of X bar. The expected value of X bar, 1.3. Oh, have we seen 1.3 before?
Yeah.
1.3, that's also the expected value of x. So, right, x bar fluctuates, but on average, so what, fact number one, it's not coincident that expected value of x bar is always mu. Okay? We're not here to prove these facts. We're just here to make sure that you're aware of these facts so that we can use them later. Next, I want to calculate variance of x bar. Variance x bar is a x bar square minus mu of x bar square. Okay? So go ahead, get this number for me. Value for E of x bar square yet?
1.735.
735?
1.735.
1.735. You get a confirmation, guys?
Wait, no.
Yes, no?
Is it 1.995?
1.995.
Yeah.
Yeah.
1.995. .995. 1.995. Okay, so then variance of x bar is 1.995 minus mu of x bar square, which is 1.3 square. Yeah? I got 0.305. You get that?
Yes.
Variance of x bar. So we use this notation, variance of x bar, to distinguish from the variance of the population. Variance of a population, right? We get 0.61 earlier. 0.61. And variance of x bar is 0.305. Are they related?
Yes.
Yeah, how? How so? What's the relationship?
You take the other one divided by 2.
0.61 divided by 2. Yes? What's the 2 coming in? Where's the 2 coming from?
The sample space size.
Yeah, that's the sample size. Okay, so I'm giving you fact number 2 now, and that's true in general. That's not coincidence. Okay, the variance of X bar is the population variance divided by the sample size. Yeah. There's 2 important facts, right? Fact number 1, if you recall, the expected value X bar is the same as the population mean. The variance of X bar is population variance divided by the sample size. Always true. These 2 are 2 critically important property of X bar of the sample mean. The sample mean fluctuates. The sample mean is not constant. Mu, sigma squares are constant, but the sample mean changing from sample to sample, correct? If I go out, I collect a sample, if I go out, let's say, for example, let's say I'm studying Cao Se Fullerton GPA, GPA from Cao Se Fullerton students. If I randomly select 20 students, I look at their GPA, I average, I get 1 X bar, 2.65. If I go out and collect another sample of size 20, likely I'm going to get a different value X bar, 2.7, something like that, correct? So the sample mean varies from sample to sample. The sample mean could take values different from the original. In this case, the original population is either 0, 1, or 2. My sample mean can be 0.5. My sample mean can be 1.5, right? If the sample size increasing, I have more different value that X bar can take on, okay? Regardless, though, this is always true when I look at this, when I look at the how X bar changing. I look at the expected value X bar is always the same as the population mean. When I look at how X bar fluctuates, it's sigma square over n. Now, the second property telling me that X bar, the variance of X bar is really small compared to the variance of the population, right, of individual observation. It's n times smaller, yeah? So if I, let's say in practice, we use X bar to estimate the population mean, because in practice, we don't know population mean. We want to use X bar. I have a sample, right? If you want to estimate Cao Se Fullerton's true average, GPA average, okay? Unless you have access to 40,000 records. Otherwise, I don't know the true value, okay? So I'm going to draw a sample of size 20. And based on that size 20, I say, hey, that true average is probably about 2.65, okay? So I'm using, in practice, we're using sample mean to estimate the population mean. This second property is telling me that X bar has a variance of n times smaller than the population variance. Now, as an estimator, do you want it to have small variance or large variance? Anyone?
Small variance.
Yeah, right. As an estimator, you prefer your estimator to have small variance, so small precision, correct? It fluctuates. I know it fluctuates, but I hope it fluctuates less. So I have my estimation is as precise as possible. So, and this fact telling me that, hey, if I want more precision, I need to increase the sample size, right? The larger the sample size, the smaller the fluctuation, the higher the precision. That's what fact number 2 is telling me. Is that okay, guys? So that's what we learned from this basic example, all right? Let's look at your textbook on page. Problem 614, page 287. So here, this is my population. My population, I have 3 possible values, 0, 1, 4, and for simplicity, all of them has a 1/3, 1/3, 1/3 chance, right? 1/3 of my bags are 0, 1/3 of my bags are 1, 1/3 of my bags 4. So in part A, we want to know the population mean and the population variance. In B, I want to find the sampling distribution of X bar from sample of size 2. Verify that mu of X bar is mu and variance of X bar is variance divided by 2 again, just like what we did. That's basically the problem. So go ahead first, calculate these 2 numbers. Right. Aaron is stepping up. Huh? Okay. Man, I hate online teaching. I cannot, gosh, how you understand material without seeing your face. Okay, did anyone have a value for mu quickly?
5/3.
5/3, yes. And sigma square?
2.88.
2.88. Can I get a confirmation on 2.88? All right.
Yeah.
Okay, now let's do part B. P is where you do that big table and then small table, right? So here, this is the population, right? 1, 0, 1, and 4. 1/3, 1/3, and 1/3. From here, I'm going to draw two observations, the first one and the second one. Yeah? Okay, so I'm doing that table again. And list all the possible sample. I calculate the sample mean, X bar, and I calculate the probability for each sample. So 0, 0, 0, 1, 0, 4. 1, 0, 1, 1, 1, 4. 4, 0, 4, 1, 4, 4. Yeah, just like what we did before. I calculate the sample mean, the probabilities, and then I get the simplified table for X bar. That's the sampling distribution of X bar. Zero 0.5, 2.5, 1, 2.5, 2, 2.5, and 4, right? And everything is 1/9, correct? Because 1/3 times 1/3, right? Each point is 1/3, so everything is 1/9. Okay, so then I have, I'm gonna combine everything here to get the distribution table for the sampling distribution of X bar. What are the possible values? 0, 0.5, 1, what else? 2, do we get 1.5? There's no 1.5. 2, yeah, 2.5, and 4, yes. 0, that's the only one instance, so that's 1/9. 0.5 here and here, so that's 2/9. Yeah. 1, there's only one instant, I get 1/9. 2, there's 2 of them here and here. 2.5, yes. and 1, 9. So 3, 4, 6, 8, 9. That's that's my valid distribution table. Yeah. Okay, so now I'm gonna do part C. I'm gonna verify the two facts. Right, that mu of x bar is mu and variance of x bar is the population divided variance divided by n. I know mu. We calculated mu before. Mu is 5/3 and sigma squared 2.8 we calculated before. So now let's calculate mu of x bar. That's expected value of x bar. Okay. So I use this table right here. Yeah. 0, 1, 9, 0.5, 2 9s, etc. 4, 1, 9. Get something like 1, 1, 4, 1, 4. So I got 15 9. Did you get 15 9s?
Yeah.
And then divided by 3, so I get 5/3. Is that the same as mu? Oh yeah. Yes. So fact number 1 verified. I need to calculate this number. That's variance of x bar. X bar square minus mu of x bar square. Mu x bar 5/3. So I'm calculating E of x bar square. So 0 square 1 9, 0.5 square 2 9s, 4 square 1 9. That's what I'm waiting for. Something over 9. For EX bar square. I got 38. Did you get 38 over 9?
Yeah.
Mhm. So 38 over 9. And this number is nothing but 25 over 9. So that's makes it 13 over 9. About 1.44. 2.88 over 2. Yeah. Is that okay, guys? So that's verified. So we see again, the first example we saw that scenario. Second example, that's still true. So it's a true fact. They are true facts. We didn't prove it here, but we prove it in other classes. But we need to know them so we can use them. Okay. Let's take a 5 minutes break, and then I'll go back and talk about the next topic. 5 minutes. So be back in 5:36. Okay, let's see. Let's get back here. The next topic is called the central limit theorem. CLT. The central limit theorem. So what's the problem? Okay, so let's say here's my distribution just like before. 0, 1, 4, 1/3, 1/3, 1/3. We learn how to find the sampling distribution of X bar when the sample size is 2. Then I get the table like this, right? So I can put a subscript 2 there, represent that that's the distribution X bar when the sample size is of size 2. Now suppose that instead of sample of size 2, if I draw a sample of size 25, okay, I want to know how X bar is distributed. Well, when sample size is that large, I cannot sit there and list all the possible sample anymore, right? In this case, how many possible sample? Are there? Well, it's 3 times 3 times 3, 25 times. So that's 3 to the 25th power, okay? It takes my whole life, right, to sit there and list all the possible samples and calculate the sample mean and the sample and the probability. No way, I'm not going to do that, okay? I'm not wasting my time like that. So how do I then answer this question? That's the spirit of central limit theorem, that's CLT. So CLT said this. When n, right, so this is CLT. When n is sufficiently large, actually, the larger the n, the better. That's what this means, sufficiently large. When n is sufficiently large, X bar, the distribution X bar is approximately, so I put a dot on top of that tilde sign, okay? It's not exact, it's an approximate. Normal with the mean being the mean of X bar and with the variance being the variance of X bar. In other words, X bar is normal. The mean of X bar is the same as the population mean. And the variance of X bar is the population variance divided by n. Yeah? These are the two facts that we established earlier, right? What's new? The new thing is the normality. Right? The central limit theorem say that X bar somehow look like normal. Okay, somehow look like normal. Center at mu. So regardless of what the distributions, the underlying distribution is, when the sample size is large, X bar behave like normal. Okay. All right. So how do I use this fact? Let's look at problem 630. On page 295. Okay, you guys have the problem? Yeah? All right. So a random sample of size 64, right? Observation is drawn from a population with mean equal 20 and standard deviation equal 16. So here's my population. Usually we draw an oval, represent a population. This population has a mean equals 20 and a variance of 16 squared, right? Because standard deviation is 16. And from here, I'm going to select 64 number observation. That's what we do in practice, right, when we're handling statistics. I have a new, let's say, for example, I work for a drug company, and they have a new drug, right? After testing on the lab to show positive result, the next step is to show result on animal, on rats, and then the third step is to show positive result on human. And so let's say, for example, to conduct tests on human, I say, hey, I go to radio and I say, we're developing this new wonder drug, and I need human participation. So if you if you have this disease, and please call us, something like that. So I gather 64 people, and they are testing on my drug, right, on my new drug. See if it's working or not. That's my sample right there. This is a sample, whereas this right here is my population. That's everybody in there, right? Okay, give the mean and standard deviation of the sampling distribution of X bar. So part A asks for, what is the mean of X bar? Well, from fact number 1, the mean of X bar is equal to From fact number 1, the mean of X bar is equal to
The mean of the whole set.
the population mean, which is 20. Yes? And the variance, I usually work with variance. The variance of X bar from fact number 2 is the population variance divided by the sample size, right? The population variance is 16 square divided by 64. Yes? 64 is a perfect square, so a 16 over 8 square. Yeah? And so that's 4. Variance of X bar is 4. Yeah, compared to the variance in population variance 16 square. It's 64 times smaller. X bar has very small variation compared to the population, right? Or a single observation. That's part A. Are we okay, guys? Part B, describe the shape of the sampling distribution. So X bar would vary from sample to sample. X bar would take so many possible values. Okay, in this case, sample 64, there's no way for me to construct the table like we did earlier. Yes. So in this case, I'm going to call upon the central limit theorem, right? By the central limit theorem, X bar is approximately normal. Yeah. And the mean is 20 and the variance is 4. You with me, guys? So if I have to describe the shape, yeah, X bar has a bell-shaped curve, center at 20, like this. Yes. If they ask for shape, bell-shaped curve, right? Approximately, because n is sufficiently large here. N is 64, right? A typical size of n, about if n is 40 or more, that would be considered large. All right. Any question? All right. Suppose that I'm going to go straight to part E. I skip B, C, D. I go straight to part E. So let's see how we use this fact to evaluate probability. Let's say I want to calculate X bar less than 16. Yeah? X bar less than 16. X bar, as we saw over here, this picture here, 16 is right there, right? Less than 16, so the probability is this area, correct? X bar is very close to normal, but is X bar standard normal?
No.
No, this is not 0 and this is not 1, so it's not standard normal. So if I want to evaluate this, what do I have to do first?
Standardize it.
I have to standardize it, right? So X bar minus the mean of X bar and the standard deviation of X bar, okay? Not sigma, it has to be sigma of X bar because I'm working with X bar, yeah? So 16 minus mu of X bar is 20. And standard deviation of, what is the standard deviation of X bar? What is the variance of X bar?
4,
4. So the standard deviation of X bar is
2.
2. Yes. Central limit theorem says that this ratio is approximately Z because I standardize X bar. Yeah. X bar is approximately normal. So after standardizing, it's approximately standard normal. Right? 16 minus 20 minus 4 over 2. So minus 2. Yes. So now I'm looking at the Z curve. Center 0 and negative 2. So I'm looking for this area. What's the R code for this?
P norm negative.
P norm negative 2, right? And if you do that, what you get? 0.0 I'm waiting. 0.0 0.0228. All right. That's part E. Part F, I'm looking for the probability that X bar is above 23. Go ahead. Very similar kind of calculation. Same thing. I'm going to standardize x bar minus mu x bar sigma x bar. 23 mu x bar is 20, sigma x bar is 2. So this becoming very close to z. 23, 1.5, yes? And so right now I'm looking for 1.5 bigger than 1.5. So this probability is right here. Yes? What's the R code for this?
One minus P norm of 3/2.
1 minus P norm of 1.5.
1.5.
Yes. And what would the answer be?
0.0668.
0.0668. Thank you. You can do G, whatever, right? Okay, let's look at one more problem. Problem 642. Mm-hmm. 642, 640, I'm sorry. $2.96. It's a word problem. So let's read it. Let's understand. That's the kind of things I'm going to give into you during the exam, okay? According to the American Automobile Association, AAA, the average cost of a gallon of regular unleaded fuel at a gas station in April 2007 was $2.835. We wish now, right? That's not the case anymore. Okay, 2007, $2.83.5. Assume that the standard deviation of such cost is $0.15 standard deviation, so same unit as X. Suppose that a random sample of 100 gas stations is selected from the population in April 2007. The April 2007 cost of regular, okay. Consider X bar. So let's say, here's my population. This population consider all gas station, yeah? That's all gas station, right? All gas station. And from here, I pull 100 gas station and look at their price in April 2007. Is that okay, guys? You see the setup? Yeah. This population here, we know that from all gas station, the mean, what was the population mean? $2.835, and the standard deviation is 0.15. Okay. And I select 100 gas station from there. And then from here, I want to look at the sample mean, right? What is your cost for 1 gallon, right? I look at the cost for 1 gallon of this second station. I look at the cost of 1 gallon of gas for the last station. And then I look at the sample mean, right? Add them up, divided by 100, the average. Yeah? Same thing. I'm looking for part A. I'm looking for mu of X bar. And I'm looking for the variance of X bar. Mu of X bar is equal to mu, which is 2.835. Yeah, $2.83.5. The variance is the population variance divided by the sample size. So 0.15 squared divided by 100. Right? So that's 0.15 divided by 10 squared. So that's telling me that the standard deviation is 0.15 divided by 10. You take square root of that, right? Which is 0.015. Yeah. What is the approximate probability that the sample mean is ranging between 2.84 and 2.86? Right. If I look at the sample mean of these 100, what's the chance that the sample mean is somewhere from 2.84 to 2.86? That's what I'm asking. Yes? The sample mean. The sample has a mean fuel cost. Right, that's the top of the sample mean. The sample has a mean fuel cost. So the first step, we know that X bar is approximately normal, mu X and sigma X squared, right? So if I want to find this probability, first I have to standardize it, yes? X bar minus mu X bar divided by sigma X bar. 2.86 minus mu X bar, 2.835 divided by the standard deviation of X bar, which is 0.015. So we have to get this number right? If you don't get this number right, you don't have the right denominator and everything is off, correct? You're not divided by sigma, you divided by this, sigma over root n, yes? Square root of n. The variance of X bar is this divided by n. So then the standard deviation of x bar is the square root of this. And square root of sigma square is sigma. And then, so this gives you the formula for the standard deviation. Yes? Sigma over root n. Sigma over root n, square root of n. 2.84 minus 2.835 divided by 0.015. Yeah. So then this fraction right here is very close to z. That's what the central limit theorem is saying. So I need to evaluate these two numbers. What's the first number? Aaron?
0.333.
0.333?
Yeah.
What's the second number?
1.667.
1.667. Do I get a confirmation on that, guys? Yes? All right. So now you draw your picture, right? 0.333 and 1.667. So I'm looking for this area. Yeah? I'm looking for that area. Okay. So I'm going to use all code, please.
P norm 1.667 minus P norm 0.333.
And final answer.
0.3218.
You gotta guess that? That's central limit theorem. That allows you to calculate probability involving X bar, right, when n is large. Otherwise, messy. I cannot, oh, okay, 1.6, all right. Any question for me? That's sampling distribution of X bar. We look at the first case when sample size small, then we can construct the table for X bar. But when n is large, you cannot do that anymore. You have to rely on central limit theorem. Yeah. When is our first exam? Anyone?
Next Thursday?
Next Thursday, right? Exam 1 is next week, a week from today. This is week 5. Next week is week 6, okay? There will be no quiz on Tuesday, no quiz on exam week, yeah? Only exam on Thursday. So we're going to have a review on Tuesday, right? And ask me any questions about the exam that you want to know. You want to ask any question, all right? Okay, that's all for tonight. I'll see you on Tuesday. Yes? Stay warm. It's pretty cold tonight.